Alright, so this video is about finding percent composition of compounds and then also determining an empirical formula of compounds from the percent composition. So if you're in my general chemistry class, this is page 5 of your fill-in notes that we've been working on in class. So let's go at it. So our first blanks here for, if we look at CO2, we can find out that it's 27.29% carbon, and we can find out that it's actually 72.71% oxygen. And it's a really easy way to figure out that information. To find percent composition, all you have to do is take the mass of the part that you're interested in, and you're going to divide that by the mass of the whole. And then you're going to multiply the whole thing by 100. And that's going to get you your percent composition. This is the same exact thing that we do when we want to figure out what percent we got on a test. Let's say that the test was worth 20 points total and we got 18 out of 20. This is exactly how we find our percent that we get on tests. We take, okay, I got 18 points and the test was worth a total of 20 points, and I do 18 divided by 20 and multiply by 100, and I get my percent. It's the same idea. So if we want to find the percent composition of this molecule here, what we have to do is first figure out what the whole thing weighs. So if we add 6 C's plus 12 H's plus 6 O's, we'll find out that the mass of this compound is 180.156 grams. So now we know the mass of the whole. Now we have to figure out what the mass of each part is. So if it's asking the percent composition of this compound, that means what percent of it is carbon, what percent of it is hydrogen, and what percent of it is oxygen. So that's what we're going to do next. So what we're going to do is, if we want to find for carbon, for example, so for percent carbon, we're going to do 6 times the mass of carbon, which is 12.01 grams. And that's the mass of the part, so this is how much carbon weighs in our compound, because we've got 6 carbons. So 6 times the mass of carbon divided by the mass of the whole, 180.156 grams, and then we multiply that by 100, and we'll get our answer. So for, in this case, we have 40% carbon. Okay, so now we have found out that that answer is 40% carbon. And all I did here was just multiply, I have 6 carbons in the compound, multiplied by the molar mass of carbon, get the mass of the total mass of the carbon in the compound over the total mass of the whole compound, and that's my percent of carbon in the compound. And I can do the same thing for the hydrogen. For the percent hydrogen, I have 12 hydrogens in this compound, so 12 times the mass of hydrogen over the mass of the whole compound, and multiply it by 100, and I end up getting, let's see, 6.7% hydrogen. Okay, so now I know carbon and hydrogen, and there's really 2 ways I could get the percent composition for the oxygen. I could either add 40 plus 6.7 and subtract from 100, because remember, all of these are going to add up to 100% of the compound, or I could just keep doing it the way I'm doing here. And so, let's see, I'm running out of room. So for oxygen, I would do percent oxygen is equal to 6 times 16 grams divided by the whole, 80.156, and multiply by 100. And then that would give me, let's see, 53.3% oxygen. Oop. Okay, so now I know how much percent oxygen I am. Okay, so that's what the first example was. Same idea for the second. So for the second one, the whole compound, if you add 3 NAs plus 1 P plus 4 O's, if you add all of that up, you get 163.94 grams. So if I want to find the percent composition of each part, I just have to take the mass of each part. So the percent of Na, I'll take 3 times the mass of Na, 22.99, divided by the mass of the whole, 163.94, multiply it by 100, and I'll get my percent of Na, which is 42.1% Na. And I can do the same thing for the P and the O. For P, I gotta write smaller here. There's only one P here, so the mass of P is 30.97 divided by 163.94 times 100. And I end up getting, let's see, 42.1, no, 18.9. And I don't have room to show the work, but for oxygen, you'd end up getting 39% oxygen. But I think you get how to do this, okay? So that's that. So these are pretty straightforward. It's just the same way you would find your percent on a test, okay? So that's percent composition, pretty simple. Empirical formula is a little bit different. It's not, I wouldn't say it's too much more difficult. So the first thing you have to figure out is the empirical formula of a compound is the smallest ratio of elements. In the compound. Okay, and that tends to throw people off sometimes, but let me give you a few examples. If we were looking at, for example, H2O versus H4O2, if we wanted to pick the empirical formula, it would be the one that has the simplest ratio. So between these two, which one has the simplest ratio? Is it here or here? And the answer would be here. We have a 2-to-1 ratio, 2 hydrogens to 1 oxygen. Here, this ratio is doubled, so it wouldn't be the simplest ratio. Another example that you might see, if you had CO3 versus C3O9, this is a 1-to-3 ratio, and this is a 3-to-9 ratio, which could be simplified. So then this would be the simplest ratio. Okay, so these are the empirical formulas. If you are multiple of an empirical formula, so if you notice this was 3 times the empirical, that's what's called a molecular formula. So this guy over here, I don't know why I drew it like that. This is a molecular formula. Okay, and this would be a molecular formula as well, because if you notice, if we multiply this by 2, if we multiply this formula by 2, we would get this formula here. So like H2 multiplied by 2 would be H4, and then O times 2 would be O2, so we just multiply by 2. So this is another example of a molecular formula. Where it's not the simplest ratio. Okay, so simplest ratio is the empirical, okay, and then the any multiple of that would be your molecular formula. Okay, so that's the difference. So if we want to find an empirical formula, you can actually do it given the percents, or the percent composition of a compound. So if we want to do this, the first thing we're going to do is assume 100 grams of compound. And then from there, you're going to divide each by their molar masses. And then the next step is kind of long, and it doesn't make much sense in words, but it makes more sense when we do it. But here it is. You're going to find the element with the smallest number of moles and divide all other moles. Ooh, I'm running out of room. By that number. Okay? I swear that will make sense in a second. Just hold on with me. And then the ratios that result will be the subscripts for the formula. Okay. Whew. Okay, so these steps don't really make much sense in words, but let's do an example and this will make a lot more sense. So we have a compound that is 65.5% carbon and 5.5% hydrogen and 29% oxygen. And from this information, we can actually figure out what the formula for that compound is. So the first thing, what we're going to do is assume 100 grams of this compound. So if we had 100 grams of this sample that was 65% carbon and so on, if we had 100 grams of it and it's 65% carbon, that would mean we would have 65.5 grams of carbon. It would basically just turn all of our percents into grams, which is helpful. So the first thing that you're going to do is assume 100 grams of a compound, and then essentially what that allows you to do is turn your percents into grams. So that's what we're going to do first. So we're going to do, so this is going to turn into 65.5 grams of carbon and 5.5 grams of hydrogen and 29.0 grams of oxygen. So that was step 1. And then it says step 2, divide each by their molar mass. So that's what I'm going to do next, is divide each by their molar mass. So 1 mole of carbon weighs 12.01 grams. And that answer, let's see, that gets me 5.45 moles of carbon. And then here, 1 mole of hydrogen weighs 1.008 grams, and that gets me 5.45 moles of hydrogen. And then 1 mole of oxygen is 16 grams, and that gets me 1.81 moles of oxygen. Okay, so that was step 2. Step 3, it says find the element with the smallest number of moles and divide all the other moles by that number. So let's look at our answers then. We have 5.45, 5.45, and 1.81. So our smallest number here is 1.81. So what I'm going to do is divide each number by 1.81. So when I do that, I'm going to round to the nearest whole number. That's going to be 1, obviously. This is going to be 3, and that's going to be 3. So this means then, when we write our formula, our compound is going to be C3H3O1, and we don't write 1, so it's just going to be that. So that is going to be our empirical formula for this compound. Okay? So you can do this if you start with percents, or sometimes they'll just give you the grams and not the percents, which basically just saves you a step and you can just start off at step 2. Okay? So I'll do one more practice problem and go from there. So let's see. Okay, so we've got our percents, and the first thing we're going to do is assume we have 100 grams. So we're going to turn these percents into grams. So we essentially just remove the percent sign and make it grams. This is not 3.9, it's 39. 39.9 grams of carbon, and then we have 6.7 grams of hydrogen and 53.4 grams of oxygen, and do the same thing. So that was what we just did with step 1. Now we're going to do step 2, divide each by their molar mass. So 1 mole of carbon divided by 12.01 grams, and that gets us 3.3. And then 1 mole of hydrogen is 1.008 grams, and so that ends up getting us 6.6. And then for oxygen, the same thing. 1 mole of oxygen is 16 grams, and so we end up getting 3.3 moles of oxygen. And now we can do the same thing. So now we've gotten into moles, and we look for the smallest number. So we have 2 of the smallest numbers, so it doesn't really matter which one you pick. Just divide by that number, divide by 3.3. So we end up getting 1. This is 2, and this is 1. So then our complete formula will be C1, H2, and then O1. And we don't write 1, so it's just that. Okay? So there's that. Let's see. So this is not actually in your packet. I'm going to add one more example here. So what did I add? I added another problem. Bear with me for one moment. Okay, so let's pretend for a moment, we have our empirical formula here, so we're going to keep working with that. And let's say we have, so a molecular formula, or an unknown substance with empirical formula CH2O has a molar mass of 60 grams. What is the molecular formula? Okay, you might encounter a few questions like this in your homework. So if you see a question like this, basically this means that we know the empirical formula of a molecule, but we don't know its molecular formula. We don't know if it's been multiplied 2 times over, 3 times over, 4 times over. We don't know what the ratio is here that it's been multiplied by. So we know the empirical formula. We know that basically its simplest ratio is going to be, in this case, this. But we don't know if it's going to be 2 times this, 3 times this, and so on. So what we can do, this is a really simple one-step thing, is you're going to find the molar mass of your empirical formula. So CH2O, if you add that up, you end up getting 30 grams. Okay? So this means our unknown weighs 60 grams. So our unknown is 60 grams. We're going to divide that by our empirical formula mass of 30 grams, and we get 2. That means that our molecular formula is 2 times our empirical formula, so our molecular formula will be C2H4O2. And that's that. Okay, so that's the last example that you would need to know to do your homework. So if you guys if you have any questions, come in at lunch. End of the marking period is coming pretty soon, so if you are missing stuff, this was from like last week or 2 weeks ago, so if you're still missing stuff like this, make sure you get it in. So, hope this helped.